Good morning, good evening, good afternoon, good day, as they say in Australia. Today we're going to be talking about three things that are fundamental to the game engine. One is resource management. The second one is we're going to introduce kind of sprites and textures, and we're going to build a heads-up display. As always, I am Juancho Buchanan, and it is my pleasure to be your guide today. What are we going to do in more detail? By the end of this class, you should be able to explain why a resource manager is going to be useful in your game. In fact, you'll be able to explain why it's absolutely necessary. We're going to implement a heads-up display, which we can use for showing scores, debugging, etc., etc. And then you're also going to talk about how in our particular game engine, we tell the render system to display an object either as a colored rectangle or with textures, and you'll see how that fits into the ECS framework. One of the things that we need to do is implement a missing texture fallback so that if an artist fails to add a texture to the game, then we can see it. We'll talk a little bit about the blackboard. We'll talk about world space coordinates versus screen position and why the HUD uses screen position. And we have different coordinate systems. And then at the end of this, I want you to be able to start thinking about what is an engine level system and what is a game level system. And as we said before, we're building a game engine, but in order to build a game, you also need to add some game level systems. Where are we heading? By the end of this lesson, by the end of this class, you're going to have an engine that loads textures, renders sprites, and displays a live heads-up display. And it also handles missing assets gracefully, all through ECS with a resource manager. The other thing I want you to think about is, for a game idea, I want you to decompose it into components and systems. What happens every frame? The systems change things in that loop, and the entities that we are going to be adding to our game need components. Again, that's that spreadsheet thing that we had, where we had each entity is a row, and then the systems are code that operate on those entities, and then the render system takes all of those rows and displays them to the screen. So that's what I want you to be thinking about as we head into this class today. I'll be right back with section 1. And we're back. So, Resource Manager. Why are we building the Resource Manager? A little bit of a reminder of speed within a computer. The speed at which the CPU can read data depends on where the data is. We're going to use a baseline of this, which is if there's data in the random access memory, RAM, we can roughly, 50 gigabytes per second is roughly what a modern computer can do now. This is our baseline. A very, very fast SSD is 16 times slower. A regular SSD is 100 times slower. And a hard drive, a spinning hard drive, which probably none of us have on our computers anymore, is going to be 500 times slower. What does this mean? If we were to load a 1 megabyte texture from an SSD at 60 frames a second. So let's say that the SSD, we can read at 500 megabytes per second. So that means it's going to take us 2 milliseconds to do that. So we're going to, this is going to blow our frame budget, right? We only have so many milliseconds to work. So that's not going to be good, and we lose our frame rate. Now, what do we do about this? Oh, let's remind ourselves, first of all, that even once you get into RAM, there's these other layers here. We've already talked about these layers here and why we're using ECS laying out our data. But what we're trying to do now is we're trying to make sure that most of our data that is on disk or SSD when we start playing our game, that we actually put that data into RAM such that this particular path here can happen as fast as possible. What is the problem? Well, there's two problems. The first one is that loading from SSD is quite slow. For just a second, let's pretend that loading from SSD is not that slow. But if we try to naively use a texture in several places of our game, so for example, if we had a player that is in the game, and then I'm going to use that in a particle system, and then I'm going to put an image of my player on the UI system. So I've loaded 3 copies of this into RAM. And one of the things that you'll do with like large games is you want to have as many assets as possible. So this is a bad idea. This is also a bad idea. So we're going to replace this pattern here with this pattern here. We're going to have a resource manager, and we'll go through the code in a second. But basically the key is that we have this function here called load texture, this method. And that takes a name of a asset as a file name. The first time we call this, the resource manager goes, oh, you're asking for player.png. I don't have it. So I'm going to go to the disk and I'm going to load it into memory. And once I'm done with all of that, I will send you a pointer to this texture here so that now text1 has a pointer to this texture. The second time I load it here, the resource manager says, oh, you're asking for player.png. I have that. And so that's a cache hit. So now what we do is we take that cache value here and we return it to here, right? I can have 2 different variables here that are pointing at that texture, and it turns out that because my resource manager is very, very, very smart, I end up with this relationship being true. So the benefit that we have here is that we're going to have 1 disk read, 1 memory copy, and we have on subsequent loads very fast access to those resources, which is exactly what we want. So let's step through the implementation of this. I encourage you to go through in the game and look at the code that's actually in the game. This is all the code that we'll talk about right now is pulled from that. So our class declaration, or our interface, if you're thinking about it from a Java perspective, is we're going to, we've defined our resource manager to accept 2 construction time parameters. This is the important one here. You'll notice in our code going forward that we have an assets directory in our game. We need to have a destructor so that we can release all of our assets. And the one thing that we're not going to allow is we're going to say, I don't really want multiple copies of my resource manager, so you can't copy it, right? I don't want to copy it. And we're going to provide 2 methods, and we'll use those in this class. The first one, which we've already talked about, is a load texture, and the second one is a font. And so the font takes a font name and a font size, and we'll talk about this. But basically, this loads files, and stores them such that you can get the font. We'll use this in our heads-up display. And again, the STL render, the constructor takes the STL render and the assets directory path. So the private members, we're going to keep a pointer to the renderer. We're going to keep a pointer to the assets directory, and then we're going to have a place where we store our textures, and we're going to place a store that we store our fonts. We're also going to have a pointer to a missing texture. We'll talk about that in a bit. And then we're going to create, have our checkerboard texture here so that we're not relying on any external images. Okay, so load texture. What does load texture do? It's actually quite straightforward. The beauty of this decomposition is that it's just adding one layer. So what we're going to do is, the first thing we're going to do is we're going to add this path. So we have defined that our textures are going to be in our assets directory, in a directory called images, plus the name. Now, what I will do at that point is I will check with my cache to see if I have that file in memory. If I don't have it, if I do have it, I just return it. I've got it, it's done, I'm done. Otherwise, we load this from disk. Now notice this is our image load texture that we saw before. This is how we only have one, and then we call it. We say load this. If that texture is not on the disk, this will return, this will be a null value. So here we check to see, is this, if this texture does not exist, i.e. this is null, then we are going to return our missing texture, right? So we've simplified the code here a little bit. You can look at the code in the game and you'll see that. If we did find our, if we did find the texture, we cache it. So we're going to add that to our cache, and then we return the texture. So what's going to happen here is, if I have a missing texture, every time I call for that missing texture, I'm going to attempt to read from the hard drive, which will slow the game down a bit, but at least we're going to get a texture here that is returned, so the game can continue, and you'll see, and then you'll be able to see, oh, that texture is missing, so do that. So again, so what do we do here? We construct the full path, and again, we have decided for our particular game engine that we're going to have in the assets directory, we're going to have an images directory, and we're going to add the name. If we find that in our cache, we go, okay, we're done, we've returned it. And otherwise, what we do here is we try to read it from disk. If we fail, we return a pointer to the missing texture. So this load texture is guaranteed to always return a pointer to a texture that can be used by the system that's calling it. The font loading is similar. I did not build in a failback, a fail-safe mechanism for the load font. If you load texture, we're guaranteed to always return a pointer. I made the decision just to help illustrate how different systems can behave differently, is that the load font has no failback, so if you miss the cache and you can't read it from disk, you're going to return a null pointer here, right? But the pattern is exactly the same. Fonts live in the asset directory, in a directory called fonts, and they have a name, and that name has a colon following it here with the size. Now, when we're running with the image, for example, this is obvious, but it bears repeating. Is before caching, I had 30 milliseconds of load time. After caching, I have 10 milliseconds of load time. So this means that my frame rate time has gone down. Now, when we're all done, Remember that with C++, you have to destroy, you have to give back to the operating system any resources that you've required or requested. And so what we're going to do, we're going to do these things in reverse order, right? So first thing we're going to do is we need to know a deep delete. So the Resource Manager has a list of all of the textures that it has loaded, and it has a list of all of the fonts that it has loaded. So we destroy all of those textures. We use the STL system there, and since we're using the TTF system for the font, we close those fonts, right? So that's basically our deep delete, our destructor that goes through and deletes all of the resources that it owned. And now in the game, we need to destroy our local variables in the reverse declaration order, right? So first thing we do here is we allocate a renderer, then we allocate the resource manager. We have our game loop that goes around and around and around like that. Boop, boop, boop. The game's going, player's done. And so now what we do is we destroy the resource manager with this call here, where we go in and tell the resource manager you're done, and then we ask the renderer to destroy itself. The critical rule is if you have to delete things in reverse order. In this particular case, your resource manager must be destroyed before the STL renderer. Right? Okay, we'll come back after this to talk about the heads-up display. Okay, let's talk about HUDs. HUDs are heads-up display. It's a term that's used in the aviation, particularly fighter pilots, where they're on a task, so they need to be focused on seeing what's happening in the world, but there's also relevant information like the speed or the altitude that they need to reference in order to make decisions. So we're going to do the same thing in our game engine. We're going to add the capability to do that. Typically, there's two types of HUDs. The one is one that we give to our developers, which has frame per second, has optimization data and stuff like that. Then the other stuff that we will put on a HUD is the score. This is relevant to the developer and to the user. So instead of providing two HUDs in this particular class, we're going to make one that has developer information, which is this here, and then we're also going to have the user information. Once you understand how the HUD works, you can split these into two, and then you could toggle them individually. So let's have a look at the HUD that you get with this particular class. So here's the most exciting game ever. So what you are is you are a gem retriever. And what you're going to do is you're going to go through this very, very dangerous blue world, and you're going to go to the right. See, my character can move. Now notice that I have my character moves, and here I've got there. So my character has intersected with this particular object here, so I've discovered this gem. Now what happened there was that the state of the world changed such that I now have the score of my game is 1 right here. My frame per second is changing every frame because my computer is doing all sorts of things. And I also have this information down here that allows the player to know what to do. The other thing that I can do, I look at this and I go, oh, I can move. I can move. I can also toggle my HUD. Oh, let's try that. I'm going to hit H. Oh, look, my HUD went away and my HUD came back. So I can toggle it and stuff like that. So that's what my HUD is. That's what we're going to be building for in this particular section. So let's go have a look at it and see how that works. Basically, we're going to think of two different coordinate spaces. The game world, which we're building, is going to have a much richer coordinate space. You can move around, you can zoom, pan. We'll introduce cameras in a future class. Everything's relative to the world. Right now, we're going to fix our HUD for now. For the rest of the course, this is going to be true, is that our HUD, our screen space, is going to be fixed to the screen. And so what does that mean? If you think about driving a racing game where you're driving around on a track, you're seeing buildings coming towards you, you're seeing cars driving beside you, all of that stuff. But on the bottom right, you may have your speedometer, and that's in screen space. It's unaffected by the camera movement, and it's always relative to the screen corners. So we'll come back to this when we introduce cameras. How are we going to build our HUD? We're going to build it as a first-class ECS system. So what is a system? If you remember, we have this spreadsheet with rows, and every row has components. And so our ECS HUD system is going to look for entities or rows that have text and screen position, right? Again, our systems are testable. We don't want to do this. We don't want to have a standalone HUD class. We want to have a consistent framework where we have HUD elements are entities. So if I want to add a new HUD element, I just create an entity, and I'm not modifying a class, right? So our HUD components are the string. We need to know what's the string that we want to display. We need to actually know what kind of font we're using, and we need to know the size of the font, and we also need to know the color, right? Apologies about the formatting, but text wrap. We also need to have a position for this entity that is a HUD component, right? So our coordinate system, we're going to use the bottom left origin, which we're already using. Our world has exactly the same coordinate system right now. As I said, we will enrich our world coordinate system in a later class, but for now, this is 0, 0. And so I chose that so we have the same coordinates as the game entities that we have right now. We will actually do that. One thing that we should mention, which is already in the code, we've done this for rendering rectangles or text, so we have to do the same thing for our text, because SDL thinks that this is 0, 0, and we think that this is 0, 0, right? So we just have to implement this formula here, and that allows us to put the text in the right place. So, our text rendering pipeline. You are very familiar with working with code, and you just say system.out, and it prints to the console. But what's actually happening is that your text is being converted into a bitmap, which is then being rendered into your texture, into your terminal application. So the text that you see here is not actually text, it's a bunch of bitmaps that you're seeing in this one here. So the process that we use with SDL is we have to load the font, then we have to take the text and we have to convert it into a surface that's here. And then the next step is we convert that surface to a texture, and then we can draw that texture at the desired position. There's a lot of work to get text here. You never knew that. So even when you're looking at this PowerPoint presentation or a terminal, that is exactly what's happening underneath there, okay? So the API details is this one creates a surface, this one destroys the surface, and then this one gets us the texture size. So we can actually, once we have rendered the texture, we can see how big it is so we can actually frame it. We use the height for the position. So here we are. What we're going to do is every frame for every entity. So I've found an entity for the HUD, and I'm going to load the font. I've hard-coded it to default TTF here, but you would read that font from your entity. And the color, again, you would read from the entity, but for simplicity's sake, I've made it white here. And again, here, my text, that's going to be coming, that will be in the entity, but here I'm going to just hard code it. But here's the crucial thing is this is a cache call, so except for the first call to this, it's not really costing me anything. This here is where we create the texture that STL can display to the screen. Once we display this texture, we clean up our memory. We get rid of this one, right? We get rid of this right away. You only hold on to memory as long as you need it in C++. And then here we apply the Y flip, and then we call STL render texture, and then we will destroy that texture. You can see you can look at that up in the code. So here's my HUD system. It's going to take the STL render right here, and it's going to take the ResourceManager, and I'm going to have the window height and the window, the width and the height, right? And then I'm going to have a render call. So my HUD system is a read-only system, and it needs access to my components, the entities, and it also needs access to the blackboard, right? And so and then privately I store the STL render, the ResourceManager, and I store my window width and my window height. So my my render step for my HUD system is going to look at the blackboard, and it's just basically going to decide whether the HUD is visible or not. If I am not visible, I return. So all of these other entities that are part of the HUD, I just skip over them at that point. And then, so if I am visible, I just look for any entities that have text, and then I look to see if that entity has a screen position, and if that's so, then I go through and I do the work that I showed before. So for each entity with both text and screen position, so back here I hard-coded all of the steps, and here we can see how we're getting that data from the entity, right? So I basically here I load my font. Now, as I said before, I have no fail-safe here. You could, if you wanted to, and it's an exercise that I would recommend you try. It's not part of any assignment, but this is part of your exploration. If you can't load this font, how would you add a default font such that, a default font, and would you change the message? So I personally would put, make this code here display string no font found for that, and then you can go find it. But anyway, so go ahead and play with that if you want. So if we can't get a font, we exit. We then try to convert it to a surface. This again is an error. If I can't do this, then I'm just going to continue. And if I can't get the texture, I'm going to continue. So basically, all of these failures are not documented. You'd have to think about how you're going to debug them. The reason that I did it this way is that the font management for our particular purpose is very simple. We're not going to have a lot of complicated fonts. And then now here we do the flip. We get the texture size here. Then we do our conversion, and we get our destination X and Y. And now I render my texture into my rectangle, and then I immediately destroy my texture. Now notice that here we got rid of our surface, and then here, right here, we destroy the texture. So we have to do that per frame because the string may change. Okay, that's it for our HUD. Okay, so in the last class you made you added a bunch of things that bounced around the screen, exciting rectangles. We're going to add a new level. You've already seen it, but here it is. I now have textures. So this little character here has just found these 5 gems in the most exciting game ever, which is to find 5 gems on the screen. So how are we going to do that? What we're going to do is we're going to add a new component called images, right? So images is going to be the component that our render system will use. And what we're going to do is we're going to say, if you have an images component, we'll render a texture. If no, then I'll render a colored rectangle as before. So my images has an array of images, but wait a minute, we're storing strings. That is correct. We don't store textures in this component. We store file names, which the Resource Manager will manage for us. So I don't have to deal with loading images in here. I just have to keep the names. I also need to keep the index of the current image that's associated with this entity. And then I'm going to use this file names at here to get the active index, and I'm going to this allows me to do bounds check access. If I do for some reason if my active index becomes corrupt, it's going to throw an exception, and I can go and debug it. So why a vector of file names? You'll need multiple textures. You might be animating your frames, so you might want to have a walk cycle. You might want to have a sprite that it looks like it's idling versus jumping. You might have a wall that you're breaking, and so there might be some components on that wall where it's healthy, it's damaged, it's destroyed. So what you can do very quickly is you can just change that active index, and all of the textures for that component, that entity, are in memory. So if you just have a single texture like we do, we're going to just construct it with a 1-element vector, and so we're never going to change this number here, right? So it's going to be just fine. So the pipeline for this, apologies for it's quite small, but I'll walk you through it. This is basically, does the entity have a position? Nope, we're out of there. Do we have an image component? Yes, we do. Then what we're going to do is we're going to call the Resource Manager to load that texture. If we loaded that texture, then we will display that texture. If we display the texture, otherwise we're going to display a checkerboard fallback. If we do not have, if we don't have any images, we look down here and we say, do we have a color component? We don't have a color component. We're out of there. We don't do anything, right? So that's our flowchart for rendering there. So let's have a look at this in code. Here's our filter for entity. In entities, do we have a position size? The first thing that we're going to look for is the size. If we have a position without a size, nothing to render. So when you're doing your filtering here, you kind of want to look for the most powerful way to filter. There may be multiple elements in our game that have size, but they may not have, they don't have, sorry, there may be multiple things in our game that have position, but don't have size, so we will skip those here. And so now we ask for the position, and now we ask for the size to make sure we have it. And then now that we have a position and a size, then we continue. And so here we go here. This is what's next. If I have images, then I get my image component from my storage, and then if that is successful, then I get my texture from the Resource Manager. And see this here, you notice that we're getting the string from here, and then I draw the entity with that position. This is where we're going to do the flip, and then here is where we fall back to drawing a rectangle. So the draw entity, we're going to do the same Y flip that we did before. So the draw entity is in my render system. We've seen this before. It constructs the information that it needs here, right here, and then we go, and if we have a texture, we call STL render texture. You'll notice that that's exactly the same call that we had for our fonts. Otherwise, we render with the draw color here, right? That's what we do. Now, I mentioned earlier this missing texture fallback. If you fail silently, it's going to be really difficult to debug when there's a missing texture. So I've added a feature which is the missing texture fallback. It won't crash. You'll get this horrible texture in your game. In fact, what you're going to be doing is, as one of the exercises in this class, is you're going to be adding a new entity to the game that has a non-existent texture so that you can see what it is, and you'll be able to see that. You can see very, very quickly that so you'll add a new gem that has a image that is not valid, and therefore when you discover it, you'll see this instead of seeing a gem. So we have actually, you'll find this code in there. I'd like you to just read it, but basically what we do is, instead of relying on having a texture on disk, that is the ugly texture, or the texture that says there is no texture here, which I just provided this code here, which basically builds a ugly magenta checkerboard, and so you can go through and you can read all of that stuff. So this is quite standard. Unity uses a magenta square. Unreal is a checkerboard. Godot has some sort of placeholder icon. Our engine has a magenta and black checkerboard. So you can see that the texture is missing. Again, why don't we just return a null pointer? I want the game to continue to work. In particular, we may have a level that's waiting for artists to add assets to the game. So I can actually work on the interactive part of my game, whereas if I return a null pointer, I will do a crash. As I mentioned when we talked about the fonts, fonts will silently disappear. And so if you're going to be doing a lot of work with fonts in your game, I would recommend refactoring the font part of the Resource Manager to return a visible no font found. So you could just use the default texture there as well if you want to. It's entirely up to you how you do that. Okay, that's it. Next we will talk about our new exciting game that you've already seen. Okay, let's make a game. This game is going to be the story of an intrepid explorer, fearless explorer, who's going to travel east looking for wealth and riches. And as he travels east, he will see in the distance these red squares, and when he lines up exactly with them, he will see that they are actually gems. Now let's play the game. So here's our intrepid explorer, and he's starting to head east. He goes in this direction like that. When he can see directly in the direction of this gem, it is revealed to him that this is a gem. So what we have done here is we have changed this entity here, when it started, was identical to this one, which is a red square. So our entity had a color, not an image, as for all four of these. And then our intrepid explorer keeps traveling east. If he goes back west to tell people about his adventures, he can say, hey, I found 2 gems. And it said, well, there might be some more, so why don't you run and find some more? So he runs all the way to the east, and he finds all of the gems. And our score has turned into 5, and our explorer is happy. He's world famous, and he goes back to teach at a university as an anthropology professor. There's probably a better movie of that story somewhere else, but I'll leave you to discover that. So let's have a look and see how we built this. This is our conceptual view of what we wanted to do, and here is a screenshot of what we managed to do. So let's have a look at it. So the first thing that we need to do is set up our player. Our player is going to have the following components. We are going to give our player a position. We're going to give our player a size. We're going to give our player a velocity. We need the velocity component because we're also adding an input component, so our movement system can manipulate our player. And we're going to give our player an array of images. In this particular case, we only have one image, so our array has one element, and the index for which image is going to be displayed is set to 0. That's our player. That follows up from everything that we've done so far. Now we need to set up our gems. They are all going to start as red squares. So what we're going to do is we're going to store the gem entities in an array, and then we're also going to have a map of what gem name should be associated with each gem. We're going to pass this into our reveal system. So each one of our entities gets a position, they get a size, they get a component which is a color. Notice that we are making it red. There we go, that's our red one. And then we're going to generate the name of our gem textures. You can look this up in the code in a second. And then every gem starts with color, no images, so they all render as identical red squares, and that's what we saw at the beginning there. So what do we do now? We set up our HUD elements. This is straightforward. We're going to have an entity for our HUD FPS. Then we're going to have a HUD score. This is all being set up so that our HUD can display them. Our gem reveal system, this is different than a game system. This is different than an engine system. So in this particular case, we can tell our system which entities to operate on, so we don't have to do the filtering. And when you go read the code, you'll see that. So what we're going to do is we're going to tell this system, this fellow here is your player. These are the entities that we are going to be searching for. And by the way, here is a pre-computed list of names of textures that you're going to assign to the gem when it gets discovered. As with all systems, we have to provide an update function, and then we're also going to implement this horizontal overlap. This is a function that determines whether AX and AW overlap with BX and BW. It's totally testable. So the update system so our gem reveal system is now going to be incorporated into our game. So what we do is we ask for the player's position and size, and then for each gem we get its position and size. Then we check to see if the player and the gem overlap. If it is overlapping and the gem has color but no images, so when our player overlaps a gem and it has color but it doesn't have images, then we're going to remove the color component from that entity and we're going to add the images component. Notice that we're just doing a data change here, which is going to be picked up by the render system because we now have images. And so the next frame, when the render system renders this entity, it will render it with a texture instead of an image. So what I'd like you to do now is I'd like you to pause the video, and then I'd like you to go and dig through the game reveal system in your editor, read through the implementation, have a look and see how it iterates over the known gem list. We don't have to do a search. Make sure you understand the horizontal overlap check. We will be doing more complicated intersections in the future, and then look and see how we do the color images swaps. So come back when you've read it. Okay, I'm presuming that you've come back just to help you. The horizontal overlap, which is a pure function, is going to basically check one of these two conditions. So basically, this and this overlap when neither is entirely to the left or the other. So basically, this and this, if both of these are true, then it is an overlap, right? So you can draw it out on a piece of paper and see how that is and stuff like that. So here's the tests that we can generate for that. Again, draw these out on a piece of paper and verify that this code here makes sense to you. So at this point we have we have to talk about game level versus engine level systems. So the game reveal system is a game level system. We're going to put it under game, not engine. So when you build a game, the expectation is that things like movement will probably be in the engine, and things that are game specific, in this particular case, it's a reveal system. If it's reusable, in general, you put it in the engine. So our render system is reusable, our HUD system, which we developed in this class. The movement system, this could be in the engine, this could be in the game. If your movement system is very specific to your game, you might want to move this from the engine into the game level. Again, there's no correct way to do this. The input system, this is generic because all it does is it adds the keys that are pressed to the components that have the input component, so that one makes sense. The game reveal system is game specific, so we're going to put it in the game, right? So the engine code doesn't depend on the game code, but the game builds on top of the engine. So this is what our game looks like. We are going to process our input events. We're going to do the input to velocity, so our player control system runs. then we run our movement system, and then we run our game gem reveal system. And that's our loop, and then we just keep going around and around and around, about like that until we quit. We render the game. We do the background. We render the game, so we clear it to the background screen. We render the game, then we render the HUD afterwards. Notice that we render it in these two orders, and then we call our time frame end, and then we update our blackboard. Right? The render pipeline, let's blow this one out a bit. We clear it, so we make sure that we start with a clear screen every frame. Then we are going to go and look for all of our entities. We will look for entities that have images and color, and then if we have an entity that doesn't have either color or images, we skip it. Notice that here we're going to be searching for these entities. We're not hard coding them, so that's why it's a general one. And then our HUD overlay is going to look for, first of all, to see are we visible? If so, then what we're going to do is we're going to look for entities in our entities that have the text and screen position, and then we present the buffer to the screen at the end of that. And so the architecture of our game that we built in this particular class, we have main CPP that is using all of these systems over here. We implemented a ResourceManager, which is used by the RenderSystem. It's also used by the HUD system. And then we've also have a gem reveal system. Now notice that the gem reveal system does not actually use the ResourceManager, because what we do here is we just use a name of the texture. We don't actually load the texture. So we're deferring that use of the textures for the gems and for the player to the render system here. This is what our project directory looks like now. Okay, so what we need to do is we need to start thinking about games in terms of systems. So we're going to go through an exercise here, just kind of briefly. We're going to think of the game. So what I'd like you to do is describe the game in one sentence. For now, we're going to be thinking about kind of simple games, but you'll get the idea. And then what we need to do is we need to figure out what exactly is going to happen every frame, because we have this game loop that does input, and then we do a whole bunch of systems down here, and then over here we have a rendering, and then we go back up and come back into here again, right? So what we need to do is we need to think about what's happening every frame. The beauty of the ECS architecture is that it reduces the design to just how can we think about what's the current state of the world and what I need to update for the next system. And so that's what these systems are going to do. So think of it as instead of a spreadsheet, we have a big kind of on the wall, we have a working system with all of the components and all of their entities, and then people come into that room, they look at those entities, and they make some adjustments, and then at the end of the day, that updates the what's on the screen. But the instructions that you give all the people that come into the room are very specific. You're going to just come in, look for entities that have these properties, and then you're going to do some changes. So let's walk through this with a well-known game, Breakout. As I said, I will actually publish it as another repository for you, so you'll be able to have that. But let's have a look here. Describe the game. A ball bounces around the screen. The player moves a paddle left to right to deflect the ball upwards. when the ball hits a brick, the brick is destroyed. If the ball falls below the paddle, the player loses a life. One sentence, every design starts here. Again, this is not a course about game design, but it's as you think about building the game engine, you do have to understand how to describe games. So I probably won't design any fun games in this course, but I will show you how to design games. The fun is up to you. What happens every frame? So we have this game with the paddle breakout, and so the paddle is moving left or right. We in the same way that we move the player left and right, we have a velocity. We have the ball, which has velocity. It changes based on bounces or collisions with bricks. So we have to do the collisions with the ball versus the walls, the ball versus the paddle, and the ball versus the bricks. And then we need to have a system that destroys bricks. We need to update the score if we're counting the number of destroyed bricks. And then we need to draw the paddle, the ball, the remaining bricks, and the HUD. So every verb is a candidate system. So every thing that changes is a candidate system. So what are the things? Our things are the paddle, the ball, an array of bricks, a wall, and the content of the HUD, right? And the components, so the components are going to be the kind of all of the components that are here are define the game. So position, size, velocity, color, input, destructible. So basically we're going to add a component that says this thing is destructible, right? And then so that way we know that we can actually destroy it. We already have most of these. So the one that we're going to do is the destructible. Our systems are get the input, move the paddle, move the ball, check the collisions, destroy the bricks, update the score, and render the system. So they're kind of all independent, all fairly simple pieces of code, which will lead to a emergent game, which is actually quite a bit of fun. So the frame, here's our game loop, or the frame loop, which is this is what happens every frame. We do the input, we update the player, we do the movement of all the things that happen to be moving. We do the collision system update, we do a destruction system update, we do a score system update, we render we clear, we render the game, we render the HUD, and then we present. And then we come back and go back and do that again. What I would like you to do as part of the exercises for this class is I'd like you to pick a game. It can be one of these games, or you can any game of your own. Don't pick a game that's too complicated. Try to pick some sort of, pick the game. If you're playing a game on your phone right now, pick that game and then kind of go through this exercise. What is changing every frame, and what do the entities have to have? So in order for these systems to act on these components, that's how you're going to describe what's happening in your game. And what would be the system execution order? No inheritance code. It's not an object-oriented. Resist the idea to try to build objects. Think about just data and systems that come in and manipulate that data. Okay, so let's wrap this up and then we'll talk about what's next. So we talked about the Resource Manager. The Resource Manager is going to give us the ability to have resources managed in a central location. We are going to use dependency injection. Please go read the code for that. I want you to, as you wrap up watching this video, open up your IDE and go read the code for all of these things. We implemented a HUD as an ECS system. HUD elements are entities, right? And they're identifiable with text and screen position. Image rendering. We're going to extend the render system, and we're going to check to see if there's images. We'll see in the future how we could use this array of images to show animations. So we actually added images as an array so we don't have to change it in the future. If we don't have images, we check for color. We showed how to have a missing texture fallback. You can go and change the ugly checkerboard for something less ugly. We talked about keeping our assets in memory so that our game can run fast. This is the second time we've talked about performance. We're using ECS to increase the availability of the data to our CPU and GPU. We're also going to use a system to make sure that our assets are in memory so they can be fetched fairly quickly. And then this class we started to think a little bit about there are going to be some systems that are game specific, and there's going to be some game systems that are engine generic. And so we'll keep growing that over the course of this course. And finally, the preview for the exercises. We talked about the missing texture fallback test. So what I want you to do is I want you to add a sixth gem to this game. I want you to add a sixth game, and then you can see that the non-existent texture will show up as a fallback texture. I want you to modify the score to display. The purpose of this particular exercise here is to have you read the HUD, and then once you understand the HUD, I want you to add a win message when all gems are uncovered and write a unit test for the win condition. Again, this is to have you understand how we are using entities within the HUD. And then as part of thinking about games, I'd like you to pick a game and decompose it into the components and systems on paper. And then I want you to take photographs of that or scan them. And there's a little written analysis that I've asked you as well. So that's it. I hope that you have a great week and look forward to seeing you at the next one.